We are Dream Team Vink VOS, and we will discuss the RCSP problem today. To the note that we're going to the next slide, you will hear this sound. Right, so today we'll give you a brief problem definition of the RCSP problem. We'll show you how we try to solve it using our approach. We'll give you the performance of our algorithm. We'll show you what kind of results we could have, and we'll give you a brief conclusion. Right, so we are given a graph with edges and vertices. And within this graph, we need to try to find the shortest path from S to T, while the amount of time is under the time constraint. So you can see, for example, here is the graph. We've got the distances on the first part of the comma, and then the time is on the second part. And this is then over the arc from S to 2. And then our aim is to try to find the shortest path from S to 6. This can be any other path, and the point of the algorithm is to find the shortest path while it's under the time constraint. Right, so our algorithm can be dissected into 4 parts. We've got part 1 where we find the shortest path of the time and the distance from S to T. Our part 2 is where we try to prune the graph to delete some nodes on edges. And part 3, we implement the lambda path finding algorithm, which is based on the Lagrangian relaxation. And in part 4, we use endpoint optimization to try and even further improve this path. Right, so part 1. In part 1, we try to find the shortest path by using Dijkstra. Now, we already know Dijkstra, so we're not going to go into too much depth with this algorithm. But it is essential to know that this part gives us, this returns a path from S to T, given a sort of constraint, given that we're going to use either the time shortest path or the distance shortest path. Right, so now let's try to explain the pruning of these graphs.
Ja, netjes. Okay, thank you, Joshua. Now we're going to part 2, where we're going to prune the graph. So what do we mean by pruning? Let's have a look at the graph. So suppose this is our graph. We have lots of nodes, and we have a source node S and a destination node T. Now what we see is this graph is so big that probably many nodes we're not going to use anyway. So these we may as well prune. Because we do not know exactly what our resource constraint shortest path will look like, but it will look more or less like this, like the purple line. Which means that the vast majority of nodes we are probably not going to use, so we might as well cut them away. How do we do it? How do we cut nodes away? How do we know which nodes we're not going to use? Our first method is double Dijkstra pruning on time. So why do we call it double Dijkstra pruning? It is because we perform Dijkstra twice. The first time we take node S as our source node, and we fill the graph with values for LSV, which is the shortest time path from S to V. And the second time we do Dijkstra, we take node T as our source node, and we also fill the graph with values for LTV, which is the shortest time path from T to V. So for example, let's have a look at node V, where we have LSV, so the shortest time from the shortest time path from S to V is 8, and from T to V is 7. That means that every path from S to T going via V is going to have a time of at least 15, 8 plus 7. And this exceeds our time limit of 12, hence we know for sure that V is not going to be in any feasible path, so we might as well prune V. Then we also have double Dijkstra pruning on distance. So it's again called double Dijkstra because we do Dijkstra from S and from T, so twice. But now we do it for distance. Okay, now recall that Joshua talked about the time shortest path. So the shortest time path from S to T. This time path has a certain length. And we know that this is already a feasible solution to our problem. And it has a certain length. So we know that any path which has a greater length than the time shortest path, we're not interested in that also, because it's going to be worse than this feasible solution that we already have. So by that logic, we're going to prune many nodes as follows. So for example, let's look at node V, where we have the shortest distance from S to V is 5, and the shortest distance from T to V is 6, and the distance of our time shortest path is 8, and 5 plus 6 is 11 is greater than 8. So we're not going to be interested in any path from S via V to T because it's already worse than the solution already got, so we cut away V. Okay, and there comes our third method of pruning, which is the dead-end pruning. Because if you look carefully at the instances that we were given, there are many dead ends in the graph. What does a dead end mean? Suppose we've got node S here and node T here. Then the blue node, in this case, is a dead end. And we're never going to be interested in a path going to this dead end and back, because the distances on every arc is positive. So going into the dead end and back is always going to increase the length of the path unnecessarily. So we're going to cut away the blue node, but also note that if we cut away the blue node, the red node will also have become a dead end node because it only has one neighbor. Therefore, we're going to have to prune the whole dead end chain, so to speak. And we do that for the whole graph. That is dead end pruning. Okay, so we prune the graph, and then one may ask, how many nodes are pruned? Like, does it really make such a big difference? Well, yes, it does. For example, let's have a look at New York, where we had 3 queries, query 0, 1, and 2. And before we did any pruning for each query, we had 264,000 nodes. And in the first query, we only had 57 nodes left after the pruning. In the second query, we only had 3 nodes left after the pruning. And in the third query, we only had 63 out of 264,000 nodes. So pruning does make a very big difference.
Oh, yeah.
Yeah, no.
Perfect. Thank you, Wout, for a lovely explanation on how to pre-prune a graph. With this pre-pruned graph, we will now try to find a solution to our RCSP problem using the Lambda pathfinding algorithm. This Lambda pathfinding algorithm is heavily based on the Lagrangian relaxation. This is where we introduce a new cost to every edge in our graph. With all these costs in place, we try to find the cost shortest path. But how do we actually compute this cost? Well, the cost of an edge E equals to the distance of E plus time of E times a certain lambda. Now, how do we determine this lambda? So, if, for example, our time of this shortest path is really high, we would increase our lambda so as to get time more dominating over the cost function. So we would get a shortest path from S to T, where because time is more dominating, we would minimize the amount of time we have in the path. So our aim is to find a balance between the time and the distance of this path. So we get a nice convergence between the two of them. So where the time is rightly dominating and the distance is also rightly dominating. But first, how do we get this lambda and how do we converge? Right, so the lambda we can compute by introducing 2 shortest paths. One is the distance shortest path, denoted by PD, and the time shortest path, denoted by PT. Now, we know from these 2 paths, the total cost of this path can be computed by the distance of path time plus a certain lambda times the time of the path T. The same we do for the distance shortest path, then we get this nice equation. Like I said before, we try to find the perfect balance between the time shortest path and the distance shortest path. So we set them logically equal to each other, and then by doing some algebra, we get that the lambda equals to a certain fraction. With this lambda, we can then further compute our algorithm. Right. So now we get to the heart of our algorithm. This is where we essentially do the loop. So we already said lambda is computed by a certain fraction. Now we introduce this a new path R, which is the cost shortest path. So we use the same cost function as before, and now we try to minimize the costs. So if the time of this path R is smaller than the time constraint, then we know that time needs to be less dominating this path because we already have completed the time constraint. So we need to decrease our lambda. We do this by setting our path of the time equal to r. So we make time less dominant. So we would put the path of the time in the denominator. This would in turn lessen the lambda. However, if you, for example, have a time of r which is higher than the t, then we know, oh, we need to make time more dominating to decrease the amount of total time of this path. We do this by increasing a lambda, so making the time more dominant. We know it is converged when the cost of the path r equals to the cost of the path pd, because then essentially we have the equation that we had before, and this is then also our stopping condition, and in the end we return the path pt, because we already know this is a feasible path, and we would then also have the convergence complete within this path. Right, so this is the pseudocode of our algorithm. We first have the initializations here, path pd and path pt. So if the time, so we now go through the trivial cases of this algorithm. If the time of the path pd is smaller than t, the time constraint, then we already know, oh, the shortest distance path is already perfect. It's already a feasible solution. So we already know that the distance shortest path is correct. However, if our time shortest path is higher than the time constraints, then we know there's no solution available because the shortest time to get from S to T is already trespassing the time constraint. So we know there's no solution available. And then we have the heart of our algorithm again, where we compute the lambda and we set the cost of this new path r, where we create a new path r, which is equal to the shortest path regarding the costs. And then we have the case where if the time of the path r is smaller than the time constraint, and the other one is where the time of this new cost shortest path is bigger than the time constraint. And then, like we said before, where the cost condition is equal to each other, this means that the path has converged, and then we return with pt. Right. So does this actually work? Well, actually it does, because we found a case where the lambda path-finding algorithm finds an even better path than the time shortest path, which is already a really good solution. So this would actually mean that the lambda path-finding algorithm is better in some cases. But however, can the ant colony optimization create an even better solution? This is where we'll continue on.
Thank you, Joshua. In part 4, we're going to talk about ant colony optimization. Okay, so from the last part, we already have a solution. We have a good solution, a feasible solution, given by the lambda path-finding algorithm that Joshua just explained. Now we're going to try to find an even better solution by using insight from the ant world. So let's first talk a little bit about ants. Ants are very good path finders. Ants, so what are ants? Ants are very stupid, but they are with many and they communicate. And by this, an ant colony can perform very complex and very efficient behavior. Let's have a look how they do it. So ants, what they do is they communicate via pheromones. Pheromones are chemicals. And let's see what they do. Suppose we have an ant nest right here, and we have a food source right there. So we have two pictures, A and B. In the beginning, the ants have no idea where the food is. So what the ants do, they just walk around arbitrarily. And that's what we see here, they just walk in all directions. Then what happens is at some point, some lucky ant is going to bump into the food source right there. The ant is going to be very happy because he found the food. And the ant is going to walk back. And happy ants produce pheromones. So this ant that is happy for having found his food source walks back, and while he's walking back on his trail, he pisses these pheromones on the ground. And then the next ant from the nest will smell these pheromones and will follow the path. And like this, more and more ants will go to the food source, and each ant will also add even more pheromones to the path, so that at some point all ants will reach the food source by just following the pheromone path. That's how pheromones work. Another thing to know about pheromones is that an ant that reaches the food is happy, and the happier the ant, the more pheromones they produce. Let's have a look at an example. So we have picture A and B. In picture A, we have the nest right here, the food right there, and ants are reaching the food in two ways. But this is a very short path, and this is a very long path. So ants who take this path are going to be a lot happier than this path, because this is a much easier, much shorter path. So the ants on this path that are going to walk back like this are going to piss a lot more pheromones. Hence, after some time we get to this picture where all ants will follow the strong pheromone paths and go like this. So the key part of this slide, ants, the happier they are, the more pheromones they piss. Okay, now in ant colony optimization, what we're going to do, we're going to use these insights to see if we can find better solutions than the lambda path finding algorithm. So what do? We let the ants walk over the graph. So in the graph, we can see the S as our ant nest and T as our food source. Okay, so ants are going to start walking from here, and then hopefully they're going to find T, and once an ant finds T, they're going to put some pheromones on the path that they walked. And what's important to know is ants follow the pheromones, but there is also some randomness involved. Because like this, ants will just coincidentally take new paths, and hopefully some ants will be very lucky and find an even better path than the ones before. And then this better path will get even more pheromones, and then ants will start to choose this new, better path. And also, we're going to give the ants a head start, because what we saw a few slides earlier is in the beginning, ants usually just walk around arbitrarily, but we already have a very good path, which is the lambda path. So what we do in the initial pheromone network, we already put some pheromones on the lambda path to help the ants out. So let's have a look. How exactly do we create our initial pheromone network? Okay, we do it in 4 steps. So the first step is on all arcs, because pheromones are put on arcs. On all arcs, we just put one pheromone. In step 2, as we talked about, we give them a head start by putting some more pheromones on the lambda path. So we look at what the lambda path is. It is in this case the light blue line. And the arcs that are in this path, we're going to increase the pheromones by 1 more. And for the next 2 steps, we first have to look at pointing arcs. And what do we mean by pointing arcs? Recall that in the networks that we were given, arcs come in pairs. What does it mean? If we have an arc from U to V, we always also have an arc from V to U. Now, if we look at one such a pair, we can sort of say that one of them points towards T in the network, and the other one puts away from T. And what we're going to do is we're going to put more pheromones on the ones pointing towards T, and so that, because we want to sort of guide the ants towards T, so it makes sense to put more pheromones on the arcs that are pointing towards T. Okay, how do we know if an arc is pointing towards T or not? What we do, we look at U and V, and we look at the value LT of U. Recall, LT of U means the shortest path distance from U to T. Okay, so suppose that the LT of U is 10 and the LT of V is 7. Then if we go from U to V, we get apparently closer to T. Hence, in this case, the blue arc is pointing towards T and the red arc is pointing away from T. And we can do this for both the time and the distance. So for this arc, there is for this pair of arcs, one of them will be the distance pointing path towards T, and the other will be the time pointing path towards T. And usually they are actually the same. So let's go back to our picture. So we already discussed part 1 and 2, where we put 1 on each arc, 1 pheromone, and we increase the lambda path arcs by 1. And in steps 3 and 4, for each arc pair, in step 3, we in each arc pair we look at the arc that is pointing towards T in terms of distance, and this arc we +1 the pheromones. And in part 4, we're going to look for each pair of arcs at the one that is pointing towards T in terms of time, and we're going to increase that by 1. And then in the end, we will end up with this initial pheromone graph. And then you may ask, why did we choose this exact procedure to create the initial pheromone network? Well, it's just we just tried out a bunch of methods, and this turned out to be the best. Okay, now let's have a look how we can visualize what this ant colony optimization looks like. So here we got a graph where we look at instance R2000. On the x-axis we see ants. So this is the first ant, then the second ant, and this is ant number 5000. And on the y-axis we see distance, the distance of the path that this ant walked. Now there's a lot that we can see in this picture. First, in the first 1000 arcs, or the first 2000 arcs, we see that many ants, they sort of it seemed to sort of hit their heads against some ceiling. Why is this? Because in the beginning, ants just walk around pretty arbitrarily, and many of them will have very long paths. And also what we had in our procedure is at some point, if the distance gets very high, and it's about, we sort of put a threshold right here, then we abort the ant, we kill the ant and it stops. So that's in the beginning. We see a lot of ants that are a path that is too long, hence they are killed. But we do see a lot of these outliers, and these are actually one of the few ants that do reach T. So every ant that reaches T right here, they put pheromones on the graph, on the network. And then what happens? More and more pheromones are being pointed towards T. And at some point we see that indeed the ants walk better and better paths. More and more ants are actually reaching T. And the distances are going down, so the ants are indeed finding better and better paths. And at some point, they all converge to one path, which is the best path that they found. And then at some point, there are going to be so many pheromones on this path that pretty much all ants walk this path. So this is the visualization of what ant colony optimization looks like. Okay, so it's all very nice and dandy, but the question may arise, does ACO indeed make things better? Yes, it does. For example, a typical output is the one from Washington DC, where we go from node 0 to node 956. What we see, the distance shortest path is 11,700, but it vastly exceeds the time, because the time is 23,000 and the time of the distance shortest path is 25,000, so it goes over it. The time shortest path, which is sort of our initial solution, is 13,200, and then our lambda path improves that considerably by going to 12,400. And the ants colonization, they find a path which is even better by more than like 130. So we indeed find, okay, and the ants do indeed find better paths. Okay, now let's have a look at the performance of our algorithm. So our algorithm meaning first time and distance shortest path, then lambda path finding, then endpoint optimization. Okay, first note that the distance of our distance shortest path is always going to be less or equal to the optimum, because often the distance shortest path is going to be infeasible, but it has the shortest distance of all. Then we're going to have optimum, which is the path that is feasible, that is the time is under the time limit, and then comes our approximation algorithm. Okay, so from this obvious inequality, we get to this, that 1 is smaller than or equal to the optimum divided by the distance over distance shortest path, because optimum is going to be bigger than this distance. Then, if we multiply both sides by the algorithm, then we get an algorithm smaller than or equal to the optimum over this factor that's bigger than 1 times the algorithm. And then we can rewrite it by saying that our algorithm is smaller or equal to the output of our algorithm divided by the distance of the distance shortest path times optimum. What does it mean? For each particular instance, and that's what we're going to look at now. For each distance, we have the distance shortest path, and we have the best found, so our algorithm path. And we can compute this ratio. And then, by the previous slide, our result is going to be within a factor 1.098 of the optimal solution. So with this ratio from the previous slide, we can give a very precise bounds on the performance of our algorithm for each specific query. And we see that in many cases it's very close to 1. It's 1.098. Some cases it is actually 1 if the distance shortest path is already feasible. So this is how we can get an idea of how good our algorithm is indeed and how close it is to the optimum. So to give you an idea of these ratios, because each query gives its own ratio, the median was 1.2375 and the average ratio was 1.19, which is pretty decent. Now let us shortly comment on the running time. Our algorithm, our approach of all these things combined that we did, so time shortest path, distance shortest path, the pruning, the lambda path finding, and the end colony optimization, it is all upper bounded by the big O of n squared log n to the power 4.
Ja.
Kun jij dat? We maken dat kut van
Right, now we'll briefly discuss what a result of our algorithm could be. So we have an example of our DC query. So we found a shortest path with a certain distance and a time. Right, so how do we get to the end of our project? Well, we first started with pre-pruning our graph. With this pre-pruned graph, we then found a first solution using the lambda path finding algorithm. With this shortest path that resulted from the lambda path finding algorithm, we created it as a basis for the end colony optimization, which then even further improved the path of the shortest path. And our total algorithm runs in big O of m squared log m to the power 4. But most important, which really sticks to this project, is that we maximize the fun we had and we maximize our learning experience. I would like to really thank you for listening, and I hope you had as much fun as we had. So if there are any questions, we'd like to know.